Definite integrals, and I told you what to do if you have integral from 0 to 4, square root of 2x plus 1, 2 dx. 2 dx was already there. Many people ask why we did not have to have 1/2, because 2 was already there. It's a different example than from before. When you perform your substitution, you are required to change limits of integration. So when I chose u to be 2x plus 1, du became 2 dx. Then 0 was the lower limit of integration, became 1. And then 4, upper limit of integration, became 9, just because u was 2x plus 1. So the new integral became from 1 to 9 square root of u du. And then we knew how to integrate that. Here it is, u to the 3/2 over 3/2. From 1 to 9, and you don't go back to the original variable anymore. Did you notice that? We used to go back all the time. But since the answer is a number, 52 over 3, nobody cares how you got it. So you can just don't go back to x and plug 9 and 1, which are u equals 9 and u equals 1. That's important. You cannot plug x or t or m into u. Units should match. So that's important. So when we plug top minus to bottom, that's how we do definite integrals. We found 52 over 3. What I wanted to say why we're doing it, and then I will answer the question of many international students who said, oh, but I don't change limits of integration. Yes, that's how we taught in different countries as well. So that can be way too. But before saying that, I will tell you why we're doing this. So for example, let me steal someone's object. So this water bottle has some water. And I don't know, maybe not. You're German after all. Maybe some beer. Anyway, but some liquid, and we don't know how much. This is what this integral is. If you remember, actually, after I use, don't do this drawing because I'll show you better. If you remember, definite integral is the area below the graph. So it's some kind of area from, it was actually from 0 to 4. So from 0 to 4, here it is. This area is also number of water liquids in this bottle. In calculus 3, we're going to teach you how to find volumes. Today, in this class, we will teach you how to find volumes of other objects. But in calculus 3, we're actually going to teach you how to find volume of anything. Just a second, let me finish. So that is definite integral from A to B. The thing is, we did not know how to solve it, just like by looking at it. Square root of 2x plus 1, 2 dx. So we performed a transformation. Use substitution as transformation. Transformation that made it easier and created this new integral from 1 to 9, square root of u du. That's a different integral. So it's going to be different square root of u, looks like this, from 1 to 9. And the thing is, what we did from practical point of view, we put this water in the measuring cup. So I had this water and I poured it in the measuring cup, and measuring cup has measures. And now I knew, oh, it's 52 over 3 liters. That's too much actually, but whatever. So this is why we have to change limits of integration, because it's transformation. Not only we change the container from big bottle to the measuring cup, we also, when we pour it to the measuring cup, guess what? The height will be different. It feels like water here is like here, maybe 1/3. When I put it in the measuring cup, it might be full. So that is why it's from 0 to 4 becomes from 1 to 9, because the container changes. So your substitution is a transformation of the integral thing. Not only we transforming the function inside of the integral, we have to change where this integral is located. Units of integration, limits of integration. Yes? Yes, in calculus 3 we're going to do double integral and triple integrals.
Triple integral, but if only based on, well, technically it's a constant for the original function.
Yeah.
Triple integral is for density.
Yes, it will be super fun. So we're going to teach some in this class, but double integrals come in calculus 3. Now, why so many people approached me last time and asked, well, I don't change limits of integration, so write this down. Way 2. Yes, we sometimes teach you to keep limits of integration. But then you have to go back to the original function, original variable. In American system of education, they don't like this method. But outside, actually, many people using it. That's why many people ask me about it. Some of you took this class in different colleges, and they taught you this. So that means it depends. I will not take points off by if you're using both. So I don't mind. Both working fine, so why would I care that much? But you need to know how to do it properly. Make sure you do it properly, which is, let's do it again. It was integral from 0 to 4 as square root of 2x plus 1 2 dx. That was the original integral. You guys chose for me that u should be 2x plus 1. du should be 2 dx. This is my box. And then you said, well, can we just not change limits of integration? Okay, let's try to do that. But then integral will not look the way it used to be. It will be square root of u du. Do you understand that? U is inside of the square root, and this part is perfect du. So it's square root of u du. And then make this notation. X equals 0 and x equals 4. Basically, you're treating this integral as indefinite integral, and then at the end, you plug original numbers. So people don't like it here because you cannot put equal sign between these. That's why sometimes you will see note like this. Maybe just see it as indefinite integral square root of u du. Solve it first. We know it's going to be 2/3 u to the 3/2 plus c, because 1/2 plus 1, we did this before. And then you go back to the original notation x. U is 2x plus 1. So you're going to have, just like we're solving indefinite integral with no limits, 2/3 2x plus 1 3/2 plus c. And instead of plus c, now you can write down the bar. 2/3 2x plus 1 3/2, a bar from 0 to 4. And you have to check, does it make sense? So x equals 0 and x equals 4, then you can plug in. Versus here, you cannot plug in x into u and x into u. Again, don't mess up with units. You cannot plug in. If you want to know how many grandmothers are going in the morning to buy groceries, there'll be number of grandmothers. So you cannot put time in the grandmothers, money into grandmothers. The units matter. So that's important. When we make this transformation, you have to be consistent. Integral u du, limits from u to u. So if you have from x to x, you have to go back. You have to go back to the original notation. So you have to choose. Either you change limits of integration and then you don't go back, or you don't change of limits of integration, but then you go back. That's basically the whole point here. Does it make sense? So many of you saw this notation before, and I do tell you, you can use both in my class. But in future classes, maybe ask instructor just in case. Some people don't like the second way. So let me tell you about this transformation idea. Transformation. U substitution is a transformation. And let me show you this beautiful graph. We had a square root of 2x plus 1. The function square root of 2x plus 1 looks like this. Y equals square root of 2x plus 1 times 2. It was also multiplied by 2. I plotted it. Integral from 0 to 4 is this area. So we're looking for this area. It's like what is the space. If you try to build a garage roof, what is going to be this shadow below it, or the space below the roof? That's basically what we're looking for. From 0 to 4, from 0 to 4. So we're looking for this. U substitution helped us to avoid complicated integration. To find this area, you will have to calculate some complicated integral. So what we did instead, we perform the transformation called U substitution. I don't have to have such a long arrow, just small one is fine. That not only changed the function, now we have square root of U, and that's not the same thing. It starts from 0, let me change the color also. Starts from 0 and goes like this. This is y equals square root of U. So also pay attention, your input now is U, and output is y that depends on U. It used to be x, and y that depends on x. So now units are different, that's what I'm saying. You cannot plug 0 and 4 into U because U is not measured in 0 and 4 as x variables. And now we're looking from 1 to 9, this area. Not only we kind of stretched it, but we also lifted up. But the magic of mathematics is, since we put equal sign between those two integrals, this A1 equals to A2. These are the same areas. A1 equals A2. We're just taking the same amount of water and putting it in a different container. For example, a measuring cup. And that container is more convenient. Square root of U is easier to integrate. So we're just transforming, stretching, or shrinking the area shape so that it's easier to find it. For example, how to find some area? Well, if you break into pieces, put in the square, now we know how to find area A times B, and so on. Or triangle, or a circle, and so on. With water, it's a 3D example. But it is in transformation, so you have to make sure you change the limits of integration, or don't forget to go back to the previous variable. What do you think? Does it make sense? Or it's weird? All of this is weird. Let's do one more example, and then you actually can finish the homework. Let me show you example 2. Integral from e to the 7 to the e to the 9. This integral often shows up on the exam, the first midterm. You will see it on the exam review also. dx. Check it out. So again, I told you, choice of the U substitution and integration by parts we will have to choose. Just try and error kind of situation. Choose something, it doesn't work. Choose something else, and it will work at some point. So what do you think we can choose? I see 1 over x, square root, ln x, 1 over square root ln x. Something should be U. Don't choose everything to be U. Usually that doesn't work. Yeah, people at the end, finally. Oh, you just moved from there. I just realized. Okay. Yes, that's a good answer. Very good, thank you. Who wants to add the choice? No, thank you, good job. I just realized that you moved. You should sit closer. So, not right now, but in the future. Yes. Yes, let's choose natural log to be U. More?
And then you can make it into U over square root, or du over square root U.
Yes, that's a good one. Okay, people think I'm getting it. If you don't getting it, you're a little bit behind, so that means you should start your homework as soon as possible. Good job, people. See, the more you do your substitution, the more you get it. It just comes with experience. So, before we do this, let's make our box be ln x. Oh wait, how did you guess it should be ln x? Like how would you explain it to your friends who are also in the same level right now? Yes?
Natural log of x, the derivative of natural log of x is 1 over x.
Yes. Yeah, good, exactly. Anyone else? So this is how I explain it. U substitution works when one piece looks like a derivative of another piece. And then I see like 1 over x and the square root, no connection. ln and x, not really. ln and 1 over x has connection. Derivative of 1 gives you another one. U substitution undoes chain rule, so one piece should be derivative of another piece. Let's see, du is 1 over x dx, perfect. Check how beautiful it will be. This becomes u, whatever is inside of the square root, and this piece is a perfect du. You don't even have to do anything. Perfect du. Now, I will teach you again how to change limits of integration. And then after this, you can choose by yourself. Check this interesting notation. A, so remember integral is from A to B, right? So this is x. X is e to the 7, which is A, and x is e to the 9, which is B. So nice international notation is e to the 7 becomes. That's kind of a short notation. How do we convert it? Well, what does it become? Well, u is ln x. So it's going to be ln e to the 7. You plug it into your u. U is basically the rule. We made up a rule. U is ln x. So plugging e to the 7 into u, into ln x, gives you what? 7. Log undoes e and e undoes log because they're inverse to each other. That's why actually they were created. So e to the 9 becomes u equals blah, blah, blah. Guess what? 9. And some people remember this is a used to be e to the 7 became 7. B used to be e to 9 became 9. So the new integral after transformation becomes from 7 to 9. Who wants to tell me? People over there? Yes? 1 divided by square root of u du. Thank you. Agree, disagree? Comments, critics, questions, ideas? That's going to be the hardest part. Usually after this, integration is doable. But to find what you should be as a choice, then to actually perform it and not to make a mistake. What do you think about that? Let's keep going. How do we integrate 1 over square root of u? Somewhere at the end, people with smartphones. Somewhere at the end. Yes.
You make the 1 over square root u make it negative.
Yes, good job. U to the negative 1/2. Integrating u to the negative 1/2, you add 1 becomes what? 1/2 divided by 1/2. A bar from 7 to 9. Now we plug in, because we changed limits of integration, we don't go back. Let me check. This is u equals 7, u equals 9. Plugging into u, that is legal. You can do that. But you cannot plug u into x or x into u. Okay, my box looks like so. Plug the top minus the bottom. It will be 2, 9 to the 1/2 minus 2, 7 to the 1/2. Which is 3 times 2 is 6. 6 minus 2 square root of 7. That is the correct answer. 9 to the 1/2 is 3. For you to know, I used Wolfram Alpha to plot this, which I can show you right now. Oh, I should probably teach you how to use Wolfram Alpha. Wolfram Alpha, people, is an amazing tool. Don't abuse it too much because you might get addicted, so you always have solutions, but you should use it to check yourself, to have less frustration. But do you see what I'm doing here? Check it out. Plot. Magic. And I'm going to plot the first function, which was 1 over square root of x. SQRT is square root of x. No, it's ln x. Square root of ln x. And don't forget parentheses in the denominator. And there is an x in front of it. Plot.
Are you trying to show us something? Are you trying to show us?
Thank you. See, the front row should let me know because I don't see the screens. Okay, I did plot 1 over blah, blah, blah. And it actually knows how to plot it. It always changes to log base 10. That's because it's how it's coded. This is how it looks like. And we want from what to what? From e to the 7 to, bless you, e to the 9. And actually it will show you the area just like definite integral should be. Here it is. So let's draw this. I actually have a beautiful drawing here. Here it is. Let's recreate this nice drawing to show you how transformation looks like. The previous graph looks like so. It's 1 over y equals 1 over x squared of ln x from e to the 7 to e to the 9, keep forgetting. And this is the area we're looking for. It was not easy to integrate it as it is. So we performed a U substitution, U sub transformation, which went from x and y into u and y. Now it's going to be from u to y, which depends on u. And then change the whole integral into a very simple function. It looks like so, and the function has a name. Y equals u to the minus 1/2. Simple as that. And it's from 7 to 9, from 7 to 9. We found this area instead, but this is the same number. That's kind of the whole idea here. It is the same number. Equal. That's not a smiley face, it's an equal. That's a pretty cool idea here. So let me show you this. Square root of x while you finish. To the, if I want to plot it now, 1 over x to the negative 1/2. Don't forget parentheses. Now it's going to be from 7 to 9. It will also do the same thing. It will plot for me. It should be a little bit curved, but if you zoom in, it looks like a line. And the answer is the same. Logarithm, blah, 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 2.03. Integral, oh, the parentheses, no, looks good. So you see, Wolfram Alpha is really good. Definitely, I highly recommend. I use it all the time for teaching, checking my graphs, checking the numbers. Imaginary numbers are really good there, ratios and factorials. We're gonna do that too, and series. Definite integrals. What do you think about that? So let me show you one more thing. There is a symmetry topic which I have a video on. Just watch the video, it's easier than explaining it in class, which basically tells you, I have good notes on this, which basically tells you will see some complicated functions in your homework like this one, but you just put 0, because some functions, guess what? They have positive and negative areas, and positive cancels out negative forever. And that's why some of them are just gives you 0. And I solve some homework problems for you as well. So just check out my solutions in my notes. As you can see, sine and secant squared and so on. Number 10, number 18, I have 14 and 17 also solved. And we did some in the office hours. Average value function. I just give you the formula and you actually should be very good after this. Average value function, we do cover it in calculus 1, probably just don't remember. AVF, average value function. Average value function. The thing is, the integral gives you some kind of value, a number. So what if you want to know the average of that? Well, just the formula will be, when you find average, you just divide by the length of the interval, 1 over b minus a. Integral from a to b, f of x dx. For you to know, which is a little bit hard to comprehend until you get to many classes of calculus classes or math classes, integration is not just about areas. Integration accumulates sums. So it's sum of stuff, which just keep growing or decaying, growing or decaying. So to find the average, you just need to divide by the length of the interval. For example, here's the function, go ups and downs and ups and downs. You find the areas from A to B. It will be this huge positive area. I just make it huge. Huge positive area. Negative area. Some positive area. So what is the average then? Kind of intuitively you see probably the average will be positive But to actually find, just divide by the length of this interval, which is b minus a. When you divide by b minus a, this line will show up. And this line gives you the average. This is average. Basically, when you take Calculus 1 at ASU, has 5 exams for you to know, which is super crazy. So what is the average of your exam grade? Guess what you do? You take all 5 grades, right? So it's, for example, 78. Then second exam was 85, then 90, 98, and the final was, say, 80. You add up those numbers together, and then what do you do? Divide by 5. Why? Because 5 is the number of exams, from 1 to 5, or from 0 to 5. So 5 minus 0 is 5. So average is exactly what you think of it. What is your payment rent for 6 months? Accumulate all the payment with utilities, divide by 6 months. That's average. So how much do you pay on average? That's going to be exactly what you think it is. So now with this formula, you can do this homework. There's nothing extra crazy here, to be honest. And the only thing I wanted to show you more was this. Somehow everyone's stuck with this example. Last example. Example from your homework. It's actually number 1 from your homework. Integral from, let's make it from 0 to pi, just why not? Sine square root of x divided by square root of x. Does anyone recognize this? Right? It's from your homework. It's number 1. The thing is, we like to put this example in the midterm 1. We usually do that because it's like very visual. People usually do well. So it's just very pleasant to put it on the test. This is u substitution. What should you put as, what should you choose as u? You have sine, you have 1 over square root of x, you have square root of x in sine, inside. Again, the intuition is, like people already mentioned, some piece is a derivative of another piece. So, what should you choose u? Yes. Square root of x, but which one? Well, it doesn't matter which one, but how do you know? Someone over there? Yes? Which one? Oh, Liate is sectional integration by parts. Don't mix this up. I know what you're talking about. We're going to learn it like today, after this example. No, u substitution has this idea that whatever is inside usually is a good choice for u. So we know how to create sine of x. I don't like having sine of the function. So that's why it's a good intuition to choose this to be u and see if it works. What if you have sine of square root of x over cosine of square root of x? Then you kind of play around and see what's going to happen, you know? So usually it's undoing chain rule idea. So whatever is inside, you undo that. Let's try again. So u is chosen to be square root of x. What is du then? 1 over what? Square root of x? 2. Like so? Okay, let's concentrate. Don't sleep. So it's going to be, let's concentrate. No, good job, people. I can hear you. Bless you. Everyone is sneezing. So x to the 1/2, right? Derivative of that is 1/2, x to the minus 1/2. And that's why whoever said 1 over 2 square root of x was right. Just if you don't remember, just check yourself. Especially on the test, check yourself with a pencil. 1/2 goes down, x to the minus 1/2. Stuff like that. Okay, how about changing limits of integration or not? This time, let's not change and see if we like it or not. So, look at that. I will tell you a new thing in this case. dx. Last time I told you that either you do the way I like it, which I can see not everyone like it. So let's explain it differently. I need 1/2 1 over square root of x dx. But I have just 1 over square root of x dx, right? So I would divide by 2 and multiply it by 2. And somehow people don't like it. I can feel it's not a popular idea. But I would do like this. I would just put it here, which is 1/2. Or just even multiply by 1/2. And then multiply by 2, so it cancels out. And this will be used as du. But if you don't like this method, here's one more way to do it. Not way 1 and not way 2. It's way 2 modified. Check it out, this idea. I have dx over square root of x. So let's solve for dx over square root of x. Make sense? Let's solve for it. So, bless you. 1 over square root of x dx equals, how do you solve it? Well, let's multiply by 2. So I'm going to multiply by 2, and it will be 2 du. Does this make sense? So this box in green will go exactly here. 1 over square root of x dx becomes 2 du. So it's going to be integral sine of u, that was the whole point. And then 1 over square root of x dx, we solved for it. Here it is, here it is, here it is. So it's 2 du, which is exactly what I would do. I would divide by 2, multiply by 2. But this way, I think people get the best. Since you have dx over square root of x, then just solve for dx over square root of x from the line number 2. And then you use line number 1 and line number 3 for the integral. Does that make sense? Kind of like maybe it makes sense more than before. So I thought I should say that. If we decide not to change limits integration, put a note. This is x equals 0 and x equals pi. You cannot plug it into u at some point. You'll have to go back. Let's integrate sine. What is integral of sine? Negative cosine. How do you know? Because when you differentiate, cosine gives you negative. So it's going to be negative cosine of u times 2. Let's just put 2 outside. Not inside. U times 2. A bar 0 to pi. Can I plug 0 in pi? No. You should all say no right now. Why? Because it's x equals 0 and x equals pi. Either you have to change 0 and pi to new limits of integration, or what should we do? Go back. Go back to x. Then it's legal to, you cannot plug x into u. It just doesn't make sense to do that. So that's why this notation helps you to remember. It's x. You cannot plug x into u. So we're going to go back. U is square root of x. So it will be minus 2 cosine of square root of x. And now you don't even have to write down x equals 0 and x equals pi, because now it matches. X equals 0 and x equals pi. I will write down just to make a point. Now you can plug it in. And you will get, should have put pi squared, would be nicer then, but it's fine. Minus 2 cosine square root of pi, plug the top, minus, what is cosine of 0? 1. So it's going to be minus 2. The answer should be a finite number. See? Sometimes I make mistakes on purpose so you can catch it. And it's never my fault, remember that. Plus. Who knows why it's plus? Who can explain? Yes? Yes. It was already negative, but we plug the top minus the bottom, so it's minus minus. Good job, people. That is the last example of this chapter, 5.5. You can finish it all. Watch the video about symmetry, though. It's not very important, but it's kind of nice idea to know that symmetry happens. Well, wow, symmetry happens. What a new mind-blowing point of view. And the thing is, some functions actually are acting crazy, go up and down, up and down, up and down. But then on the left-hand side, they do exactly the same thing, but wherever it was positive, it's negative. Wherever it was negative, it's positive, and so on. And because of that, integral from the minus a to a, which is a symmetrical point, from here to here. So it should not be minus 2a to a, or should not be like minus 0.5 to a. If it's from exactly the same step size to the left to step size to the right, it will be what? 0. It's a very interesting point. So you will see lots of complicated integrals will give you 0 just because they're symmetric.